In this video, we're going to take a look at an introduction to the topic called confidence intervals. The formula is here. We don't get this, so we need to remember it in the exam. And basically what each of the things represents. X bar is the sample mean. Z comes from the normal distribution, which you've done a brief introduction on the normal distribution. You'll see more on that next year. But for now, let's not worry too much about what this bit represents. Let's actually just do the calculation. Standard deviation and a sample size. Now, when you're constructing a confidence interval, like before we get stuck into the question, essentially what this topic is telling us about, like, you know, when you wanted to know what the average of something was. So say, for example, I said, what's the average height of the male students at college? Now, obviously, if I was just asking about the average height of the males at college, if we wanted to, we could get all the males and measure them all, and that would give me exactly what the average height was. But, I mean, what if I said, what's the average height of a male in Britain? You know, you're not going to go out and measure everybody at the same time and calculate their average, are you? I mean, that's just not practical. So what confidence intervals can be used for is it's really useful to tell us about the average of a distribution. And all we have to do is go out and look at a sample. So we look at the sample mean. And just from our sample, imagine if you just like weighed 10 elephants or measured the height of 5 giraffes. Like, from taking the sample, that allows us to have a good idea about this, which is the population mean. You're never going to really know what the population mean is unless you're able to get all of the data in that population and measure it, which in real life isn't going to happen, is it? So instead we'll take a sample mean. Okay, so look at the question. It says the weight of male African elephants is known to be normally distributed, and they're given as the standard deviation of 150. So we don't need to calculate the standard deviation. Like, if they've given you the standard deviation in the question, just use the standard deviation that they give to you. Steve goes out on safari. He finds a sample of elephants and he weighs them. And we've got the weights for 8 of our elephants here. And we're asked to calculate a 95% confidence interval. So just from the 8 elephants that Steve's been able to weigh, we're going to be able to get an interval that tells us about the actual mean. Okay, the first thing we're going to do is calculate the sample mean. You might see this written in summary data as well. Like, instead of me writing all these values out, they could have just given you sum of x. So if it would have been written as sum of x, let me just calculate that. Okay, so adding them up, I get 47,200. Divide by how many there are, which is 8. And I'm getting 5,900. Okay, so that's our sample mean. But obviously we don't know, like, it's not an accurate representation, is it? Like, we've only weighed 8 of them. How do we know if the actual average is the same as this? And the reality is we don't. Like, we're going to be able to we'll go a little bit above, and what this formula is doing is we add a bit on, we take a bit off, and we say, well, that's the sample mean. If we go a little bit either side, then we can get an interval and we say, well, actually, we think that the actual mean is going to be somewhere in between those two numbers. Okay, so let's start by writing the formula. We've got x bar plus or minus z times sigma over root 10. So the sample mean is 5,900 plus or minus. The standard deviation we know is 150. The sample size was 8. So the only other thing we need to figure out is how to get this z value. So go on to menu statistics, and we want to go into distribution, normal, inverse normal, oh no, sorry, NCD. No, it is, it's been a while since this. It is distribution, normal, inverse normal. And we get this tail option. Okay, so we want to set the tail to central. And the area would be, well, if we're doing a 95% confidence interval, the area would be 0.95. Okay, so tail central, area 0.95. Leave them as 1 and 0, and then press execute. And that gives us the Z value. It spits out plus and minus, but we can just use the positive one because we're going to add it on and take it off anyway. So it's 1.95996, so I'm going to say 1.960, as long as you maintain like at least 4 or 5 significant figures, then we'll be okay in our calculation. I know it's a bit weird that we're just using this number and I've told you to press a button on the calculator, and you might be thinking, well, where's that even come from? But if you watch the video on the normal distribution, essentially where that value comes from, right, just as a little sort of extra bit of thought, if we were working with the standard normal distribution, the standard normal distribution is centered about 0. And when we're getting a 95% confidence interval, what we're trying to do is we're trying to trap 95% of the data. Okay? And what the calculator just told me, 1.960 and minus 1.960. That's the value of the standard deviation. You have to go like almost 2 standard deviations above and almost 2 standard deviations below. So if we go that far above and that far below, that many standard deviations, that would trap 95% of our data. And you will see a lot more on this next year. Unfortunately, we haven't got time to really go into detail on this now. But I mean, just for reference, highlight where this number comes from, because like if you're going to go wrong anywhere on this topic, it's going to be just getting the Z value. You're fine to calculate the mean, you're fine to do the standard deviation, you know, as long as you remember the formula. Just realise that that's inverse normal, tail central, and area 0.95. We're going to do a different confidence interval in a second, but like obviously the different area is just referencing the different percentages. We want to be 95% sure, so that's how far above we have to go and how far below we have to go. If we wanted to be 99% sure, you'll see that in a second, or maybe we'll do a 90% one. If you wanted to be 99% sure, you'd have to go further above and further below. So let me just show you that, right? If we set the area to 0.99, keep writing 0.99, so we're 99% confidence interval. The Z value would be like 2.576. So that means you've got to add more on and take more off so that we can be 99% sure. Okay. If we were going to do a 90% one, the area would be 0.9. And can you see that we don't have the 1.644, so we add a little bit less either side. So then we get like we're 90% confident in our answer. Okay, so let's go back to the normal maths menu. And we're going to do 1.96 times by 150 over root 8. And that gives us 103.94. Remember in statistics, 4 significant figures, so 6,003.9, I'm going to write 6,004. So I've just added it on there, and if I subtract it, so 5900 minus 103.94, that gives me 5796. So we should write off our answer almost like a coordinate. Like you can write it in words. It could be like from this to this. But just to get a feel for what that represents, not telling me about the individual values. Like the confidence interval tells us that we're 95% sure that the actual mean, if you went out and you weighed all the African elephants, right, we're going to be 95% sure that the average weight is going to lie in there somewhere. It doesn't tell you about the individuals. Like if you look at the individuals, that one there is not inside the interval, is it? That one there, it's not inside the interval. That one there is not inside the interval. Like we don't care about a big thing that you've got to realize when it comes to like the interpretation questions later on. The confidence interval doesn't tell me anything about the individual elephants. Okay, this tells me about the average. So I think the actual mean is going to be somewhere in between these two values. It is a 95% confidence interval, so there's like a 5% chance that we're wrong. Like if you repeatedly calculated samples and calculated confidence intervals, if you were doing 95% confidence intervals, 5% of the time you're going to be wrong. Like the mean might be, 6,005, and if the mean was 6,005, okay, I'm wrong. And like maybe Steve went out and the elephants he found were like he just found the skinny elephants, but most of the time we're going to be right. And that's the big thing about statistics. It's about realizing that it's not a definite conclusion, is it? It's all to do with percentages and also like taking a sample, okay? Because we're not going to go out and weigh all the elephants, are we? Okay, so part B says calculate a 90% confidence interval. So the only thing that's going to change here is the Z value. The Z value is determined by the area or the percentage in your test. So if we go into distribution, distribution normal, inverse normal, tail central, area 0.9, leave them as 1 and 0. That means we're going to be using 1.6448, so 1.645. So if I change this to 1.645, that tells me that I'm going to be doing I've got to add on, can you see that we're adding on slightly less than what we were previously? Because if you only want to be 90% sure, you don't need to, your interval could be a bit narrower, couldn't it? Okay, so that gives us that interval there. The next part of the question is a bit of an unusual one, especially while we're still getting used to the topic, but it's nice to start to think about what's going on with this formula instead of just like blindly plotting numbers in. Give me one sec. Okay, so it says if the number of elephants sampled was 1,000 and the sample mean X bar was still 5,900, what would the 95% confidence interval look like? Now, it's not like an exam style question, it's what would it look like? It doesn't say explain or solve, but let's just have a think about that for a second to try and understand what's going on behind the calculation that we've just done. Okay, so what we're saying here is if we took a larger sample, but the sample mean was still the same, like the sample we got for 8 was 5,900. If we went out and we weighed 1,000 elephants, but the sample mean was 5,900, would we still get an interval that looked like this? Like, would we still have to say, well, I'm 95% sure the mean's somewhere in between these two? And like, if you can't really try and think about it, just like conceptually, maybe let's look at the formula and see what would change. Like, we've got 5,900 plus or minus the 95% interval, so the Z value would still be the same. The standard deviation is still 150, but we'd be dividing by the square root of our sample size, which is 1,000. And hopefully we can see by now that that there is going to be a bigger number. So if this is larger and we're dividing by this whole thing will end up being smaller. What does that mean? If this is smaller, we've got to add less on and take less off. In other words, the interval that we'd end up with would be a lot smaller than this interval. And we can be able, and what that really means is we can be a lot more confident in our results. You know, if you've got like a smaller interval, the reason why this has happened is because when you go out and you don't, you know, if you don't just look at 8 elephants, if you look at 1,000, your sample is more accurate, isn't it? And like the larger the sample size, the more accurate your mean, your sample mean is going to be to the actual mean that you're trying to figure out. Okay. Final thing, state an assumption that you have to make. Now in statistics, they quite often ask for assumptions, like a 1 mark part of the question. And my advice on these would be if you get asked what assumption do we have to make, just go back and quickly read the question. And we'll see more on this in the later on questions. It tells us the weight is normally distributed, so that's fine. We're told the distribution that we're using. We're given the standard deviation, that's fine. And it says D goes out on safari and finds a sample of African elephants. So that's the thing, okay? In statistics, whenever we take a sample, the sample has to be random. Okay, so the sample that we've taken, we were not told that the sample was random, so we'd have to assume that the sample was random. And just think about like what I'm trying to get at here. Like, imagine if Steve could only find like the small elephants, or maybe the large elephants. The small elephants were all hiding. You know, I know it's a bit of a daft example, but like, it's a really important thing to realise. Like, whenever you do take a sample, if that sample is going to accurately represent the distribution that you're looking at, the sample itself has to be random. There can't be any bias in the values that you've taken. Like if the large elephants were easy to find and Steve could find the large ones, that's going to distort the average that we've just calculated, and it won't accurately represent the whole population with it. Okay, thanks guys.